Hey, we're talking about the unit step. First, we looked at what's the Laplace transform of a time-shifted function. So it's not just, well, you time-shift function a units to the right by subtracting off a from the argument t. So this shifts the function to the right a units. And we want to make sure if that the original in effect was cut off at 0, even if it wasn't. So this should really be f with the argument t minus a times the unit step with the argument of t minus a. That's what is depicted in the picture here. And here we said that's what its Laplace transform is. Time shifted function on the left means multiplying by e to the minus as in the Laplace domain. If we just lopped off a function to the left of a without time shifting it, just lop it off at some point a, this was the Laplace transform. Now let's talk about what if you lop it off on the right side? How do you deal with that? Well, if this were the original function and you wanted everything to the right of a gone, you want it to go down to 0, you subtract off the function that was lopped off to the left of it. So this original function, you can think of it as f with the argument of t times the unit step with the argument of t. But then I'm going to subtract off the same function that's lopped off to the left of a. So there, subtracting it off. And you can think of these things, when you see a little piece like this, you can think of it as it's a function with a starting time and an ending time. So you think of it as it's the function with u with the starting time minus u with the ending time. Here it starts at t equals 0, so it's just t. It ends at t equals a, so I use argument t minus a. And when I do that, multiply this out and take the inverse Laplace transform, this will just be big F. And this will be, by using the property we just had, property here, it's e to the minus as. I have to take the Laplace transform of this F, but with the new argument t plus a. By the way, this is, for some reason, my students have had this is one of the areas they had the most trouble with. In a way, it's not super mathematical or anything, but it's easy to get mixed up. So here's a piecewise function as an example. And we do the Laplace transform in pieces. What is this function here if it just went on forever? It's the function just plain old t, right? Function t, but it has a start time of 0 and an end time of 1. So I do this little trick again. Think of it as a piece with a start time and an end time. It starts at time 0, it ends in time 1. Now what about this piece that went on forever? That would be 2 minus t. Convince yourself of that. This is just the line 2 minus t. So that's the function that goes out in front. It has a start time of 1 and end time of 2. Here's how I deal with it. Here's how I put it as a single time function using unit steps. And now I can gather up parts, all the u of t parts, all the u of t minus 1 parts, and all the u of t minus 2 parts. So for u part, I have just a t. For of t minus 1, I'll have a minus t from here and a plus 2 minus t from here. And then finally, I have t 2 minus t in this part. That'll be a minus. Sort of multiply all that out or gather up terms. And you'll see that you kind of got lucky here. Everything is just a time-shifted function. You have an argument of t minus 1 and u of t minus a function of t minus 2 and a u of t minus 2. So these are all shifts. So we can use what property? This property. This is just good old 1 over s squared. This is 2, and using that property, it's e to the a is 1 here. E to the minus s times 2 over s squared. This is, well, this is like a 1 over s squared. E to the minus 2f. Simplified like this. Learn how to do these piecewise functions. It's easy if you think of them with a start time and a stop time. Then from here to there, you're just doing algebra. And from here to there is inverse Laplace transform. Let's see if I can do one example of this. Kind of tricky. Say here's the equation where this f is this function, this sort of piecewise continuous function. It's 1 from 0 to 1 and it's 0 after 1. And it has these initial conditions. So one thing we got to do is express this f using unit steps. So it's just 1 with a start and stop time of 0 and 1. So it's here, it's a nice easy little chunk. The function itself is just 1, so I didn't need to put that in front. So now let's take Laplace transform step by step. Since, well, let's see. This will be s squared y minus 0, s times 0, minus a minus 1 or a plus. Got the 4 times big Y. And this is 1 over s minus e to the minus s over s. Move this 1 to the right. Things over a common denominator for these two guys. And divide through by the s squared plus 4. Well, I didn't get these over a common denominator. So it's going to be 1 over s times s squared plus 4 minus just 1 over s squared plus 4. Then I have this business here. I'll pull out the e to the minus s, and here's what I have. So some of this is, I think I got to do some PFE on this guy. This will be in the table itself. If I divide by, I want it, because this has a 4 up here, I want a 2 up top, so I'll divide by 2. Keep going. It's going to be kind of long, sorry. Here's what we have. I have to do some PFE on this guy. I'm going to skip that. But it becomes this, which has this inverse Laplace transform. This would apply to both this chunk, or this term and this term. And remember, this term was just in the table already. So what do we do with this guy? How do we put all that together? Any part that has this e to the minus as thing is a time-shifted piece. So you have to do two things when you take the inverse Laplace transform. Replace t with t minus a. Then you multiply it by the unit step with t minus a as the argument of the function. This is kind of hard to get right. So let's just do the easy parts first. Things not multiplied by e to the minus s. Okay, this part is what we have here. And we wrote, actually it's this part, 1/4, 1 minus cosine theta. That's this, that corresponds to this term. Minus a half sine t, that corresponds to this term. Now we've got this guy. 1/4, 1 minus cosine 2t, but I replace every t with t minus a, and a in this case, 1. And then multiply the whole thing by the unit step with that argument t minus 1. That, and do you know what that really means? I can break it up into chunks. This part starts right at time equals 0. This part is 0 up until time equals 1. So I write this. It's good for time 0 to 1. That will still be there after time 1, but then this thing kicks in, so I subtract off that part, do that little bit of arithmetic, and I get what this means. It means this. It was all kind of a little bit tricky and subtle. Remember that. When you take the inverse Laplace transform of this part, any part multiplied by e to the minus as, you do these two things. Replace t with t minus a. In the function itself, and multiply by the unit step with the same argument of t minus a. I like that.